We've already defined a thermodynamic state of the system as an equilibrium, reproducible, well-defined state where the state functions, such as the number of moles of each component, the temperature, and the pressure, are not changing. We've said that if we can specify these functions or these variables about the system, then we have specified the state of the system. Let's think a little bit more carefully about the state of the system now that we understand things from a more microscopic perspective. Let's take a 5 microliter water droplet that's at 300 degrees Kelvin as our system. If I specify the volume and the temperature of this water droplet, you can reproduce this system at any time in any place. This 5 microliter droplet of water at 300 Kelvin is going to have 280 micromoles of water molecules, and it will have a well-defined entropy of 19.5 joules per Kelvin. Let's remind ourselves that the water molecules in that droplet are in constant motion. They're rotating, they're vibrating, and they're translating. So at any given time, my system is in a different microstate. And so over a small span of time, over the time in which I'm going to measure the volume or measure the temperature, I will have sampled nearly all microstates of the system. And thus, when I am measuring the volume or measuring the temperature of my system, I am measuring an ensemble average. In other words, I determine the value of the property for each microstate and take the average over all microstates. Any macroscopic property that applies to the entire system and does not change as long as the system is in that state is a state function. So for instance, although the energy of one of my water droplets will fluctuate in time or be different for each microstate of the system, the average energy will not fluctuate and will be something that I can apply to the entire system. In fact, the average energy is simply a measure of the internal energy. If all of my molecules are identical, as all the water molecules in this droplet are, then if I take the total number of molecules and multiply by the average energy per particle, I will get the internal energy of the system. And the internal energy is a state function because it applies to the entire system and it does not change while the system is in that state. So clearly, per particle properties, or properties of a single particle, are not state functions of the system. Another class of functions that are not state functions are path functions. We have two examples of path functions already, and they will be the two examples that we will deal with this semester. Those are heat and work. These are not state functions because they are associated with the process of transferring energy. So these functions are defined only when the system changes state and cannot be defined for a given state of the system. Put another way, the system does not have a certain amount of heat or work. It only transfers a certain amount of heat or work when the system changes state.